Okay, in this example, we're going to take another look at another two-sample proportion hypothesis testing. A study of 150 randomly selected occupants in passenger cars and 200 randomly selected occupants in pickup trucks found that 78% of the occupants in passenger cars and 74% of the occupants in pickup trucks wear seatbelts. Okay, looks like we've got two different samples here, two different ratios. We can see that 78 is more than 74, but we're going to test this out. At an alpha of 0.05 or a confidence level of 95%, we are testing the claim that the proportion of occupants who wear seatbelts is greater for those in passenger cars than for those in pickup trucks. So we're thinking about that. We're putting this greater than means that we have got a right tail test, and we're going to be looking very closely at all 5% of that alpha is going to be in that right tail. So that 95% will all be below that upper critical value. Then we're going to construct a 90% confidence interval estimate of the difference between these two populations. Okay, the deal that we're using a 90% confidence interval, we need to remember that confidence intervals are two-tailed events, and the confidence interval that will place 5% in each tail is the 90%. And we need 5% in each tail because that is the percentage that we need in the tail for our alpha and our hypothesis testing. Okay, so going on to looking and getting started with the whole process, our null hypothesis is that these two population proportions are equal. The alternative is that the population of passenger car occupants wear more, a higher percentage of passenger car occupants wear their seatbelt than our population of pickup occupants. Okay, that's what we're speculating about the population, and we're going to use this sample statistic to help us decide if we've got a claim here or not. Okay, so our confidence level is 95%, our alpha is 0.05. We talked earlier about this being a right tail test because we're assuming one is greater than the other, so it's a right tail test. Our critical value that goes with that is the 1.64, and I could have found that going back to our class activity where we're looking at a right tail test that has 95%. That curve looks something like this. So our 0.05, all 5% is in that right tail. 95% would fall below. Okay, that's going to correlate with our, when we go to do our confidence interval, we'll be using this curve where we're going to be using 90% confidence interval, where we're going to have 5% outside in each of the tails. And again, it's the same critical value, 1.64, 1.64. Otherwise, I could go to our formula page and we would use this chart here. We're doing a 5% alpha. We have a one-tail test, so that'd be 1.645. When we go to do the confidence interval, we'll be looking at this column, and the alpha level of 0.10 would have 5% in each tail, and that would again use that confidence critical value of 1.645. So 1.645 in both of these. Okay, back to all the fun number crunching. Our p-hat. Now I've got the 78% of car occupants, and we had 150 of those. So the 117, I got that by taking 0.78 times the 150 to get my 117. At this point, I really didn't need it, but when we go to do stack crunch, I'm going to need the 117. But 0.78 and our q-hat complement of the 0.78 is the 0.22. So this is the sample proportion that goes with our first sample and the q-hat that goes with that. Our second sample proportion, again, I could have taken the 0.74 that I would have gotten from here for pickup trucks multiplied by 200 to get the 148. I don't really need the 148 on paper here, but when we go to stack crunch, I'll need that. Our second sample proportion, p-hat, is 0.74. The q-hat for that would be 0.36, so we've got all that information. Our pooled sample proportion is that p-bar. It's the sum of those who wear seatbelts in both vehicle cars as well as pickup trucks over the total number of participants in both of these sample surveys. So we end up with 0.757 for that pooled sample proportion, and our Q bar is 1 minus our P bar, would be 0.243. I'm going to be using this fun formula here where I'm plugging things in very carefully. And remember, if we're speculating that the difference is equal to it, that these two population proportions are equal to each other, the difference between those two should be 0. So that's how we got the 0. I think you can see how everything's plugged in. It's definitely a challenge on the calculator, but we come up with 0.86 is our z-score for this data. Okay, so just looking at that, that's less than the 164. When we go to draw our curve here, our first method using the critical value, our z-score of 1.64, we can see that 0.86 lies below that. So this is not in the rejection zone. We go to do our p-value. The p-value that correlates with the amount of probability to the right of this test statistic. The p-value that correlates with 0.86 is 0.8051, but that's the area to the left of that test statistic, and we want to see what's to the right. So we're going to take the complement, and that would be 0.1949. So in other words, 19% of the curve would be above that test statistic. So that p-value is high, because we're only going to reject if it would be lower than 0.05. So this is high, and again, when the null is high, when the p is high, the null must fly, is that saying. Checking out the confidence interval check or method for this, we would plug into our formula for the confidence interval. And I don't believe I've made a point of that in the past, but going back to our formula, that is on the front page of our formula page. And this would be the formula here. Again, my 1 minus p hat, I'm writing q hat. It's just easier, less to write down. This would have what we had used if we had just one sample. This is what we're using when we have two samples. So going back to our formula, we plug all of this in. Again, it's a task on the calculator, but we end up with this range where we have negative 0.0355 all the way to positive 0.1155. You're like, wait a minute, how can we have this one negative, one positive? It could be that we could subtract, and it would be the other that actually would have been bigger. We could have had a negative outcome here all the way to the positive. And really don't need to make much more sense of that, other than we need to recognize that if the difference of these two sample proportions, and therefore the population proportions, if the difference of these two proportions is 0, 0 falls in this interval here. So if the 0 falls in my confidence interval, I can't possibly reject the null hypothesis. If 0 doesn't fall in it, I can't, but it does fall in here. So it could be that these two are equal to each other. So if 0's in here, it could be that they really are equal to each other. So I would fail to reject the null hypothesis. All three of these methods tell me, it's not in the rejection zone, the p-value is high, 0 falls in the interval, it could be that the difference really is 0, so I'm not going to reject saying that they're equal and possibly the difference equal to 0. So I'm failing to reject the null hypothesis. There is not enough evidence to support the claim that the ratio of car occupants who wear seat belts is greater than the ratio of the truck occupants who wear seat belts. And you're looking at it going, wait a minute, I can see that it is greater. In this particular sample, and both of these samples are really kind of small, it could be that it just falls in that margin of error, that it's on the edge but doesn't really fall into a difference here. So doing this on StatCrunch, you would go into StatCrunch. I'm going to open statistics, proportion stats, down to 2 sample, and then I've got with summary. So this is where I need to put in this information of 117 out of 150 for my first sample. In my second sample, this is my information. I have 148 wore seat belts out of the 200 pickup occupants. Okay, going to my hypothesis test, I'm assuming that they are equal, but my null hypothesis that says that they're equal, but my alternative I'm going to say that the first one is greater than the second one. We're speculating that passengers in cars are more likely to wear the seatbelt. So we're speculating that that's actually greater than. And I go ahead and hit compute, and I come up with the same z-stat and p-value that we came up with in our outcome here. Going back to our option where we're looking at confidence interval, I'm going to edit that, and I'll come down to our confidence interval. Now this is the case where I have to remember that I'm doing this at a 5% hypothesis testing. And being this was a right tail test, the confidence interval that places 5% in the right tail is a 90% confidence interval. So I click compute on that, and that is where I find this negative lower limit and this positive upper limit, and 0 falls in there. It could be that the difference between these two proportions really is 0, and so we cannot reject the null hypothesis. So all three of our methods support fail to reject the null hypothesis.